James Webb just discovered the true shape of the universe. Galaxies, too massive, too structured, and too ancient, are filling James Webb's images. They should not be there. Our best model of the cosmos, built on centuries of observation, assumed space was flat, empty, and infinite in every direction. But the data says otherwise. Space might curve. It might wrap back onto itself. The universe could have a specific shape. We will explore ancient light, holding impossible anomalies, a team hunting the geometry of space itself, and a cosmos that might be finite, folded, and far smaller than what we can see. If this blows your mind, like and subscribe. Prepare yourselves. We begin. The universe is either the most generous thing that has ever existed or the most deceptive. It has offered humanity billions of years of starlight, given us time to build civilizations and telescopes, and still refused to answer the one question that matters most. Does it end? Aristotle asked that question around 350 years before the Common Era. He was not speaking loosely. He wanted to know whether space itself had a boundary, whether there was a point at which the cosmos stopped and something else began, or whether it went on forever, with no center, no edge, no conclusion. He could not answer it. He had no tools. Nobody did. For most of recorded history, the question of the universe's shape was considered a matter of philosophy, possibly even theology, and definitely beyond the reach of any experiment a human being could design. That changed in the 20th century, and it changed because of two ideas that arrived almost simultaneously. The first was Albert Einstein's general theory of relativity, published in 1915. Before Einstein, space was considered a fixed and passive container, the stage on which matter performed. After Einstein, space was something different entirely. It curved. It bent in response to mass and energy. It could expand or contract. It had a geometry that could, in principle, be measured. The universe was no longer a neutral backdrop. It was a physical object with its own shape, and that shape was governed by equations. The second tool was the telescope, and specifically the increasingly sophisticated machines astronomers built throughout the 20th century to look at the oldest light in existence, the cosmic microwave background. This is the faint glow of radiation left over from 380,000 years after the Big Bang, when the universe cooled enough for light to travel freely for the first time. This ancient radiation is everywhere. It fills the sky in every direction, and it carries within it a detailed record of what the universe looked like in its earliest form. The patterns in this radiation encode information about the geometry of space itself. Together, general relativity and the cosmic microwave background gave cosmologists a way to ask Aristotle's question with numbers. They could measure the curvature of space. They could calculate whether the universe was open or closed or flat. They could, in principle, determine the shape of everything. For decades, those measurements pointed toward the same answer. The universe is flat, infinite, and featureless at the largest scales. The standard cosmological model was built on that foundation. Most textbooks treated flatness as essentially confirmed. Then, the James Webb Space Telescope launched in December 2021, and the data it began returning was unlike anything cosmologists had prepared for. Galaxies that should not exist, structures that formed too fast, too early, too large. An early universe that looked nothing like the simulations predicted. Something was wrong with the model, and if the model was wrong, it meant the assumptions underneath it, including the assumption about the shape of the universe, needed to be reopened. This documentary is about that reopening. It is about the shape of the cosmos, whether space curves back on itself like a sphere, flares outward forever like a saddle, or wraps around in a pattern so strange that the human mind has barely developed language to describe it. It begins, as all great questions do, with geometry. To understand what cosmologists mean when they talk about the shape of the universe, you first need to forget the everyday meaning of the word shape. A coffee mug has a shape. A mountain has a shape. These are objects embedded in space, and you can walk around them and examine their contours from the outside. The universe has no outside. There is no vantage point from which you can step back and look at the whole thing. Everything you can observe, you observe from within, and that creates a particular challenge. The only way to measure the shape of space is to examine how things inside it behave. Albert Einstein's general theory of relativity gives you the tools to do this. In his framework, the curvature of space is a physical reality that determines how objects move, how light travels, and how angles add up. The geometry of space is real, measurable, and shaped by the matter and energy within it. There are three possibilities, and they are genuinely different from each other. The first is a positively curved universe. Imagine the surface of a sphere. Draw two lines on it that start out perfectly parallel, like two meridians at the equator. As you extend them toward the poles, they converge. They meet. In a positively curved space, parallel lines that never touch in your intuition end up intersecting. Draw a triangle on the surface of a globe, and the three angles inside it add up to more than 180 degrees. This kind of space is called closed, and it curves back on itself the way the surface of a sphere does. The second possibility is a negatively curved universe. Instead of a sphere, imagine a saddle, the kind on a horse, curved upward in one direction and downward in another. In a negatively curved space, parallel lines diverge over time rather than converging. A triangle drawn in such a space has interior angles that add up to less than 180 degrees. This kind of space is called open, and it keeps flaring outward without ever looping back. The third possibility is a flat universe. This is the geometry most people learned in school, Euclid's geometry, where parallel lines stay parallel forever, where a triangle always contains exactly 180 degrees, and where space extends in all directions without bending. It is the familiar, intuitive geometry of the world around us. Cosmologists measure which of these three geometries describes our universe using a parameter they call omega k. When omega k equals 0, the universe is flat. When it is less than 0, the universe is positively curved and closed. When it is greater than 0, the universe is negatively curved and open. The closer omega k is to 0, the flatter space is. The primary tool for measuring omega k is the cosmic microwave background. The ancient light from the early universe contains millions of tiny temperature fluctuations, hot spots and cold spots scattered across the entire sky. The size of those fluctuations is exquisitely sensitive to the curvature of space. Light traveling through curved space follows curved paths, which stretches or compresses the apparent size of features in the background. Cosmologists measure those sizes, compare them to predictions, and extract the geometry of the cosmos. The measurement, when it arrived, seemed to settle the question, but settled, it turned out, was the wrong word. In the year 2009, a spacecraft built by the European Space Agency began the most precise survey of the ancient light of the cosmos ever attempted. It was called the Planck satellite, named after the German physicist Max Planck, and it spent 4 years mapping the cosmic microwave background with a sensitivity and resolution that previous instruments had only approximated. By 2013, it had gathered enough data to produce a portrait of the sky at the moment the universe first became transparent, a snapshot taken 380,000 years after the Big Bang. What Planck found, when researchers processed the full dataset, appeared to confirm the standard story. The cosmic microwave background matched the predictions of the flat universe model with extraordinary precision. Cosmologists around the world published papers treating the question of curvature as essentially resolved. The universe was flat, the standard model was validated, and then a research team did something slightly different. They looked at the Planck data in isolation, without combining it with other measurements from galaxy surveys. And what they found was startling. When the Planck data was analyzed alone, the best fit to the observations suggested a universe with positive curvature. The omega k parameter, extracted purely from the Planck satellite data, using the standard statistical technique, came out at -0.044, with an uncertainty of about 0.016. That negative sign on omega K meant the universe was curved back on itself, closed, and the signal was strong enough that it could not easily be dismissed as noise. The statistical confidence was approximately 3.4 sigma, meaning the probability of getting a result that far from zero by chance was less than 1 in 1,000. The researchers who published this finding were Eleonora Di Valentino of Sheffield University, Alessandro Melchiori of Sapienza University in Rome, and Joe Silk of Johns Hopkins University and Oxford. Their paper appeared in the journal Nature Astronomy in 2019, and it made a specific and uncomfortable claim. The Planck data, they wrote, favored a closed universe with 99.985% probability. To understand why that was alarming, you need to know what a closed universe implies. In the standard cosmological model, the universe is flat because cosmic inflation, the period of extraordinarily rapid expansion, in the first fraction of a second after the Big Bang, stretched any initial curvature away. Just as the surface of a balloon starts to look flat as you inflate it to enormous size, so too should the universe have had its curvature ironed out by inflation. Finding significant curvature would mean that either inflation did not occur in the way the standard model describes, or that the universe was extraordinarily curved to begin with, or that something else entirely was producing the signal. There was also a specific physical reason the Planck data preferred a closed universe. The maps showed a slightly stronger than expected signal from gravitational lensing, the bending of ancient light by matter as it traveled toward us. A closed, positively curved universe would contain more matter and produce more gravitational lensing. The data fit that picture better than the flat alternative. The question that followed immediately was obvious. If the universe is closed according to Planck, why does every other measurement say it is flat? The answer to that question would take years to untangle, and it still has not been fully resolved. Cosmology runs on convergence. The great triumph of the standard model was that dozens of independent measurements, using completely different physical processes, pointed to the same values for the basic parameters of the universe. Galaxy surveys, the cosmic microwave background, observations of distant supernovae, the abundance of light elements from the Big Bang, all of them told a consistent story. That consistency was the reason the model was trusted. So when Eleonora Di Valentino and her colleagues published their finding that the Planck satellite data alone preferred a closed universe, the immediate response from much of the cosmological community was to invoke the other measurements. Specifically, measurements of something called baryon acoustic oscillations. Baryon acoustic oscillations are a regular pattern of density in the distribution of galaxies across the universe. They arise from sound waves that propagated through the hot plasma of the early universe, and they left a characteristic scale imprinted in the clustering of matter everywhere. That scale serves as a cosmic ruler. By measuring the apparent size of baryon acoustic oscillations at different distances, astronomers can determine the geometry of space. When the Planck data was combined with baryon acoustic oscillation measurements from large galaxy surveys, the curvature measurement shifted dramatically. The omega K value moved from -0.044 to essentially zero, specifically to 0.00007 with an uncertainty of about 0.0019. That number was indistinguishable from a perfectly flat universe. The two datasets, each trusted and well calibrated, gave wildly different answers when used alone, and only agreed when combined. That disagreement is called a tension, and it is a tension that has not gone away. In 2024, researchers published the final analysis of the Planck satellite data, a comprehensive update led by Mathieu Tristram and collaborators in Paris. The new analysis incorporated improved techniques and reduced systematic errors. The curvature measurement from this updated dataset softened somewhat compared to the earlier result. Omega K came out at -0.012 with an uncertainty of about 0.010. Still slightly negative, still hinting at positive curvature, but now consistent with flatness at about 1.2 sigma rather than 3.4. That sounds like good news for the flat universe, and in one sense it is. The evidence for a dramatically closed cosmos has weakened with better data, but the hint has stubbornly refused to disappear entirely. The central value of omega k in the most recent analysis is still negative. It is still pointing in the direction of closure. It is just doing so more quietly than before. The current state of the measurement is genuinely ambiguous. Taken in isolation, the best Planck data hints at a slightly closed universe. Combined with galaxy surveys, the measurement is consistent with flat. Other independent experiments, including the Atacama Cosmology Telescope and the Dark Energy Spectroscopic Instrument Survey, give results consistent with zero, but with error bars large enough to include the Planck hint. Nobody can say with confidence that the universe is precisely flat. What nobody has done is prove that it is. The question of curvature remains open, and it remains open in a way that matters, because curvature is only half the story. The other half is something most cosmologists barely talk about, and it changes everything. Everything you have heard so far about the flat universe, the closed universe, and the measurement of curvature is about geometry. It is about how angles add up, how parallel lines behave, and how light bends. It is the part of the question that physicists know how to measure. But there is a second part of the question of the universe's shape that geometry cannot answer on its own, and it is arguably more important. That second part is topology. Topology and geometry are different things. Geometry describes the local properties of space, whether it curves and in which direction. Topology describes the global properties, how the universe is connected to itself at the largest possible scales, whether you can travel in a straight line and eventually return to where you started. The crucial insight is this: you can have a universe that is geometrically flat, that follows every rule of Euclidean geometry, that gives you perfect 180-degree triangles wherever you draw them, and that nevertheless wraps back on itself in a way that makes it finite. The clearest way to see this is with a sheet of paper. A flat sheet of paper has zero curvature. Now roll it into a cylinder and tape the two ends together to form a tube. The surface of that tube is still locally flat. Triangles drawn on it still have 180 degrees. Parallel lines still stay parallel. But the global structure has changed completely. If you walk along the surface in one direction, you will eventually come back to where you started. The space is finite, and it wraps around, even though locally it appears to follow all the rules of flat geometry. Now take that cylinder and bend it further, connecting the other pair of ends, and you get a donut shape. Mathematicians call this a torus. A three-dimensional version of a torus, where the universe wraps around in all three directions, is called a three-torus, and it is one of the simplest possible compact topologies for a universe. In a three-torus universe, if you traveled in any direction far enough, you would eventually arrive back at the point you started from, approaching it from the opposite direction. The universe would be finite, and it would have no boundary. This possibility is entirely within the mathematics of general relativity. Glenn Starkman of Case Western Reserve University, one of the leading researchers working on this problem, has been arguing for years that it deserves serious scientific attention. He has said that cosmologists might miss an extraordinary discovery about the universe by simply looking the other way, by assuming without evidence that the simplest possible topology is the correct one. The standard cosmological model assumes that the universe is simply connected, meaning it has no such wrapping or folding, that space extends outward in all directions without looping back. This assumption is based on convenience and Occam's razor. In the absence of evidence to the contrary, assume the simplest case. Measuring curvature near zero does not confirm that assumption. A flat measurement of omega k tells you that space does not curve dramatically in your neighborhood. It tells you nothing about whether space wraps around far beyond what any telescope can see. The topology of the universe and the geometry of the universe are separate questions requiring separate answers. And the evidence for a non-trivial topology, it turns out, has been hiding in plain sight. There is a concept mathematicians arrived at long before cosmologists needed it, and it is one of the most disorienting ideas in all of science. A space can be finite without having any boundary. It can have a definite total volume, a measurable size, and yet contain no edge you could reach, no wall you could press your hand against, no cliff you could stand at the brink of and look outward into something else. The space simply wraps onto itself, the way the surface of the Earth wraps onto itself, and every straight path eventually circles back around. The surface of the Earth is the standard illustration, and it is a good one. Walk in one direction long enough on a perfectly smooth Earth, and you will not find an edge. You will return to where you started. The surface is finite in area, roughly 197 million square miles, but it has no boundary. The analogy applies to a three-dimensional universe. If space wraps around in 3 dimensions, a traveler moving in any fixed direction would eventually return home, arriving from the opposite direction they set out in, having circumnavigated a cosmos that has no walls. Mathematicians have catalogued all the different ways a three-dimensional, geometrically flat space can wrap around on itself. There are 18 distinct possibilities, 18 different topologies that preserve flat geometry while being multiply-connected. The simplest is the 3 torus, where you imagine a cube of space and declare that the left face connects to the right face, the top face connects to the bottom face, and the front face connects to the back face. A universe with this topology would be finite in volume, equal to the volume of that fundamental cube, and it would repeat. Whatever you saw looking left would eventually cycle back to what exists behind you. Other flat topologies are more exotic. Some involve twists. In a half-turn torus, opposite faces of the cube are connected after rotating 180 degrees, meaning that when you cross the boundary in one direction, your orientation flips. You return to your starting point, but left and right are reversed. You would be your own mirror image. There are also quarter-turn versions and stranger configurations, involving combinations of twists and flips. All of them preserve the flat geometry that measurements suggest our universe has. The observational consequence of any of these topologies is remarkable and specific. If the universe's fundamental domain, the basic repeating unit of space, is smaller than the observable universe, then the same physical objects would appear multiple times in our sky, photographed from different directions at different epochs. A distant galaxy cluster seen on one side of the sky might be an image of the same cluster seen from another angle billions of years later or earlier on the other side. The universe would be smaller than it appears, a hall of mirrors in which a limited region of space generates the illusion of an infinite expanse. The critical question is whether the fundamental domain is small enough that its multiple images fall within reach of our telescopes. If it is larger than the observable universe, the echoes would never arrive. If it is smaller, they should be visible, imprinted on the oldest light in the cosmos, waiting for someone to recognize them as duplicates. 2 distinct places in the sky, showing identical patterns. That is what to look for. In 1998, 3 cosmologists published a paper that changed how scientists thought about the universe's shape. Neil Cornish, who later moved to Montana State University, David Spergel at Princeton University, and Glenn Starkman at Case Western Reserve University, had worked out a specific, testable prediction for what a multiply-connected universe would look like from inside. Their insight started with the cosmic microwave background and a simple observation about geometry. The surface of last scattering, the spherical shell of ancient light that we observe as the cosmic microwave background, is an enormous sphere centered on the Earth with a radius of about 46 billion light-years. That sphere represents the limit of what we can see. Any light that departed from the Big Bang from farther than 46 billion light-years away has simply not had time to reach us yet. Now imagine that the universe's fundamental domain, the smallest repeating unit of space, is smaller than that sphere. In that case, the sphere of last scattering would extend beyond the boundaries of the fundamental unit and wrap around. It would intersect itself. And where it intersected itself, two different patches of sky would actually represent the same physical location in the early universe, just seen from different directions. Those two patches, Cornish, Spergel, and Starkman realized, would show identical temperature patterns. The same hot spots, the same cold spots, the same fluctuations, because they are the same place. The temperature patterns in the cosmic microwave background are physical, a map of density fluctuations in the early plasma. If two circles in the sky map to the same ring of points in the original plasma, those circles should be mirror images of each other in temperature. The researchers called their paper Circles in the Sky. The test they proposed was elegant. Scan the full sky map of the cosmic microwave background, looking for pairs of circles with matching temperature profiles. If you find them, you have found the fingerprint of a finite, multiply-connected universe. If you find no circles that match beyond what chance would predict, the universe's topology is either too large to detect or simply connected. The implications of finding matched circles would be profound. It would mean that much of what we observe in the night sky is the same physical region of space appearing multiple times, seen from different angles at different moments in cosmic history. The hundreds of billions of galaxies spread across the observable universe might be a far smaller number of actual galaxies, each duplicated over and over by the repeating topology of space. Our universe would be a cosmic hall of mirrors, the same limited space casting its image in every direction, giving the impression of a vast and unrepeating cosmos when the truth would be far more compact. The search began immediately. Astronomers pointed the technique at the data from the Wilkinson Microwave Anisotropy Probe satellite, then at the Planck satellite. The results were intriguing, contested, and ultimately inconclusive. Some searches found hints of matched circles, others found nothing. The debate produced more heat than light for nearly 2 decades. But during that debate, something else was building. The cosmic microwave background itself had started showing patterns that nobody had predicted, patterns that kept appearing in data after data even as the instruments improved. And those patterns were deeply strange. In the autumn of 2003, a team of 5 researchers published a paper in the journal Nature that proposed one of the most specific and surprising answers to the question of the universe's shape ever put forward in peer-reviewed science. The lead author was Jean-Pierre Luminet, a cosmologist at the Observatoire de Paris. His collaborators included Jeffrey Weeks, an independent mathematician from upstate New York, along with Alain Riazuelo, Roland Lehoucq, and Jean-Philippe Uzan. Together they argued that the universe might have the shape of a Poincare dodecahedral space. This requires unpacking. A dodecahedron is a 12-sided solid, each face a regular pentagon. In ordinary 3-dimensional space, you can build one from cardboard and hold it in your hands. The Poincare dodecahedral space is something different and far stranger. It is what you get when you take a spherical version of that dodecahedron, where the faces are slightly curved because the space itself is positively curved, and declare that each of the 12 pentagonal faces is glued to the face directly opposite it after rotating by 36 degrees. The resulting space is closed, finite, and wildly counterintuitive. Its volume is roughly 80% of the volume of the observable universe. That means the universe, if it has this topology, would actually be smaller than the sphere of sky we can see. The surface of last scattering would extend beyond the fundamental dodecahedral domain and wrap around, intersecting itself in 6 pairs of matched circles, each pair showing identical temperature patterns because they map to the same ring of points in the primordial plasma, twisted relative to each other by 36 degrees. What motivated Luminet and his colleagues was data. The first maps from the Wilkinson Microwave Anisotropy Probe satellite had arrived that year, and they contained an anomaly, the largest scale fluctuations in the cosmic microwave background. The so-called quadrupole and octupole modes were far weaker than the standard flat infinite universe model predicted. The universe simply had less large-scale power than it should. The Poincare dodecahedral space offered a natural explanation. In any finite space, the topology acts as a boundary condition. Just as a vibrating string can only produce waves with wavelengths up to twice the string's length, a finite universe can only support oscillations that fit within its fundamental domain. A Poincare dodecahedral space, with a volume about 80% of the observable universe, would naturally suppress the largest modes, cutting off power at exactly the angular scales where the probe had found it missing. The paper set off a scientific controversy that lasted years. Some researchers searched for the predicted matched circles and found hints consistent with the dodecahedral model. Others ran independent searches and found nothing compelling. Budewijn Rukema at Nicolaus Copernicus University in Torun, Poland, led several analyses of the probe data and found tentative evidence for 6 matched pairs at an angular radius of approximately 11 degrees, consistent with the dodecahedral model's predictions. The probability, his team calculated, of that signal appearing by chance in a simply connected flat universe was only 7%. 7% is suggestive. It is hardly conclusive. The soccer ball universe remained a live candidate, one of the most mathematically elegant proposals in modern cosmology, with partial observational support and fierce opposition in equal measure. And while the debate continued, the cosmic microwave background was accumulating more anomalies that nobody had asked for and nobody could explain. Anomalies in science are uncomfortable. They arrive in data that researchers did not expect, survive the first round of checks suggesting a measurement error, survive the second round suggesting a software bug, and eventually sit there unresolved, while the community debates whether to take them seriously or wait for better data to make them disappear. The cosmic microwave background has accumulated several such anomalies over the past 2 decades. They did not disappear with better data. They became more pronounced. The most famous of these is called the quadrupole-octupole alignment. In a universe that is statistically uniform in all directions, the different scales of fluctuation in the cosmic microwave background should point randomly. The quadrupole, the largest wave pattern in the background, and the octupole, the next largest, should have their orientations scattered without any preferred direction. When the Wilkinson Microwave Anisotropy Probe satellite returned its first maps in 2003, researchers noticed that the quadrupole and octupole were aligned with each other, pointing in nearly the same direction across the sky, to within 11 or 12 degrees. Cosmologists Kate Land and João Maguijo named this preferred direction the axis of evil in 2005. The probability of this alignment occurring by chance under the standard model is less than 1%. The Planck satellite was supposed to resolve this. It was more sensitive, higher resolution, and capable of identifying systematic errors that earlier instruments might have missed. When the Planck maps were analyzed in detail, the quadrupole-octupole alignment was still there. It had survived to a new generation of instruments. The second anomaly involves the angular correlation function, a statistical measurement of how related temperature fluctuations are at different angular separations across the sky. In the standard infinite flat universe model, fluctuations should be correlated across all angular scales, including large ones spanning more than 60 degrees. The data shows something different. For separations larger than about 60 degrees, the correlation essentially drops to 0. The two sides of the sky are thermally disconnected at large scales, in a way that should not happen if the universe extends infinitely. There is also a third anomaly. The two hemispheres of the cosmic microwave background sky are not equal. One contains roughly 6% more power than the other. The northern and southern halves of the sky are measurably different, suggesting that the universe is not the same in all directions, which the standard model requires it to be. In 2024, a research team led by Gabriel Jung and Nabila Aghanim published a detailed analysis of these anomalies using the final Planck data release. Their conclusion was clear. These features are observed at a level found in typically less than 1% of simulated cosmic microwave background maps generated by the standard model. They survive updated analysis with improved noise models and corrections for systematic effects. They are real. The combined probability that all these anomalies appear together by chance in a universe described by the standard model is less than 1/10 of 1%. Physics does not casually produce results that are improbable. Either something is wrong with the analysis, or something is wrong with the model, or the universe is trying to tell us something specific about its own shape. A finite cosmos with a characteristic size would naturally cut off large-scale power above a certain threshold. That cutoff is precisely what the data shows. Something even stranger is waiting in the southern sky. Among all the anomalies embedded in the cosmic microwave background, one stands apart. It has a location, it has a size, it has a temperature, and it has so far defeated every attempt to explain it using standard cosmological physics. Researchers call it simply the cold spot, and it occupies a region of the southern sky in the direction of the constellation Eridanus. The cold spot is approximately 5 degrees in diameter, which sounds small but in sky terms is enormous, 10 times the apparent width of the full moon. Within that region, the cosmic microwave background is colder than expected by roughly 150 microkelvin. That number sounds tiny, because it is. The cosmic microwave background varies in temperature by only about 100 millionths of a degree across the whole sky. And the cold spot represents a deviation at the low end of that already tiny range. But the statistics make it significant. The probability of finding a feature that extreme, that large, and that cold in a standard simulation of the cosmic microwave background is less than 1%. The cold spot was first identified in data from the Wilkinson Microwave Anisotropy Probe satellite and was immediately flagged as requiring explanation. The simplest idea was that a large empty region of space, a supervoid, lay along the line of sight between us and that part of the last scattering surface. As light passes through a void, the universe's accelerating expansion causes a small temperature shift through an effect called the integrated Sachs-Wolf mechanism. A sufficiently large and deep supervoid could imprint a cold signature on the background. Researchers went looking for the supervoid. They found one. A large region of space in the direction of Eridanus does appear to contain fewer galaxies than expected. But when astronomers calculated how cold a spot that supervoid should produce, the numbers came up short. The supervoid is not large enough, deep enough, or empty enough to fully account for the anomaly. It contributes some of the signal, but does not explain it. Other proposals have been put forward. A topological defect from a phase transition in the very early universe could leave a cold imprint in the background. These defects, sometimes called cosmic textures, arise when a field that was uniform in the hot early plasma breaks into different configurations as the universe cools, and the boundaries between regions can leave scars in the radiation. The math allows it. The evidence for it is inconclusive. Then there is the most dramatic suggestion. The cold spot is a scar from a collision between our universe and another. In the framework of eternal inflation, the cosmos outside our observable bubble is a chaotic landscape of inflating space, occasionally spawning other bubbles that grow and expand. If two such bubbles had collided in the distant past, the collision would have left a circular imprint on the cosmic microwave background of the surviving universe. Models developed by Stephen Feeney, Matthew Johnson, Daniel Mortlock, and Hiranya Paris in 2011 showed that such bubble collision scars would appear as circular, disc-shaped anomalies in the background. The cold spot is roughly circular and disc-shaped. None of the explanations is fully satisfactory. The cold spot remains unexplained. It sits in the southern sky, colder than it should be, larger than it should be, stubbornly resisting every model designed to account for it. And it is not alone. The universe has been assembling a case against its own standard description for decades. The James Webb Space Telescope just added the most dramatic piece of evidence yet. The test was elegant. If the universe wraps around on itself, there should be a fingerprint hidden in the oldest light in existence. two different patches of the cosmic microwave background, separated by vast angular distances across the sky, should carry identical temperature fluctuation patterns because they would represent the same physical location, seen from two different directions. Astronomers gave these predicted mirror image patches a name: matched circles. In the early 2000s, the race to find them began in earnest. Bałdywan Rukema at Nicolaus Copernicus University in the Polish city of Toruń led one of the most determined searches. He combed through data from the Wilkinson Microwave Anisotropy Probe satellite, painstakingly comparing region after region of ancient sky against every other region. Every direction had to be tested against every other direction at every possible angular radius across an entire sphere of light that had been traveling for nearly 14 billion years. The computational demands were staggering. The stakes felt enormous. Then something appeared. Rukema's team found tentative evidence for 6 matched pairs of circles. Each pair sat at an angular radius of approximately 11 degrees. Their arrangement was consistent with the Poincare dodecahedral space that Jean-Pierre Luminet had proposed just years before. The statistical analysis was honest and careful. The probability that this signal arose by chance in a simple, unwrapped, flat universe was only 7%, suggestive, tantalizing, but not enough to close the debate. Neil Cornish at Montana State University ran a different search. He looked for matched circles larger than 25 degrees across the entire sky and found none at that scale. His team concluded the dodecahedral universe was ruled out, but there was a gap between the two searches that almost nobody noticed at the time. Rukema had found hints at 11 degrees. Cornish had searched above 25. The angular territory between those two numbers, the range where a real signal might actually live, remained completely untested. The map had a gap, and nobody had drawn attention to it. The debate continued for years afterward. Later releases of the Wilkinson probe data arrived, and Rukema reanalyzed the numbers each time. The signal persisted, weaker in some readings and stronger in others, but it never crossed the threshold that would silence the skeptics. Both groups were conducting careful science and reaching different conclusions from the same sky. That tension itself was worth examining closely. When the European Space Agency's Planck satellite delivered its comprehensive survey of the cosmic microwave background, the topology question received another formal hearing. The Planck collaboration in 2016 established that if the universe has dodecahedral or torus topology, its fundamental domain must be larger than roughly 97% of the diameter of the last scattering surface. That sounded decisive. For the specific shapes tested, at the specific positions assumed, in the specific orientations examined, it was. The phrase "the positions they assumed" is where everything becomes complicated. Topology searches require knowing where the observer sits inside the universe's fundamental domain. Different positions within that domain produce different patterns of matched circles. The Planck searches covered some positions thoroughly and others barely at all. Rukema and his colleagues pointed this out. The constraints were real, but they were not exhaustive. A dodecahedral universe oriented slightly differently, or scaled slightly differently, could be hiding in the data without detection. The search for matched circles had uncovered something unexpected. Finding them was hard. Failing to find them did not prove they were absent. The universe, if it was wrapped, was being extraordinarily careful about revealing its own structure. And the team that would push the search further than anyone had gone before was only just beginning to organize. In 2022, roughly 15 scientists spread across 7 countries began working together on a problem that most of cosmology had quietly shelved. They called their group the Collaboration for Observations, Models and Predictions of Anomalies and Cosmic Topology. The name compressed into the acronym COMPACT. The ambition behind it was anything but small. Glenn Starkman at Case Western Reserve University in Ohio had spent decades warning colleagues that topology was being systematically ignored. He had co-authored the original Matched Circles paperback in 1998. He had watched searches come and go, observed data improve and constraints accumulate, and seen the fundamental question remain stubbornly unanswered. Most of the field had moved on and accepted a flat, infinite universe as the obvious default. Starkman had not accepted it, and he had not moved on. The collaboration he helped build included Yashar Akrami at the Institute for Theoretical Physics in Madrid and Craig Copey, also at Case Western Reserve, along with researchers from institutions across Europe, North America, and beyond. What united these scientists was not just a shared interest in the question. It was a shared frustration with how inadequate the previous generation of searches had actually been. Prior searches had tested a handful of specific topologies in limited regions of parameter space with limited computational tools. Finding no definitive evidence, they announced constraints and closed their programs. But nobody had ever systematically mapped out what fraction of the total possible landscape of mathematically allowed cosmic shapes had been examined. When the compact team did that accounting, the answer was alarming. The fraction was tiny. The universe has thousands of possible topological shapes across different curvature classes. Science had carefully ruled out a small corner of that vast space, and the broader community had treated the exercise as essentially complete. Their landmark paper appeared in Physical Review Letters in April 2024. The conclusion was stated plainly. Prior topology searches had explored only a tiny fraction of the mathematically possible topologies, and many exotic shapes remained entirely consistent with cosmic microwave background observations. The universe could be wrapped in ways nobody had yet thought to look for. The response from the broader community was measured. Some cosmologists had moved so far past the topology question that the paper barely registered. Others acknowledged it as a genuine and important correction. Oliver Philcox at Columbia University put the situation plainly when he noted that there are many possible ways the universe could be topologically connected, and that ruling them out is genuinely difficult. What distinguished the compact effort from everything before? It was not just ambition, it was computational capacity, combined with a rigorous mathematical framework built for systematic comparison. A decade earlier, the calculations required to properly compare topology models against real observational data would have taken years on available hardware. Advances in computing and in the mathematics of cosmological statistics had made the work newly possible. They were running searches that had never been attempted at all, and in doing so, they had already found something the field did not expect. One specific version of a wrapped universe had survived every attempt to eliminate it, even when that version described a cosmos far smaller than the observable horizon. A universe where space itself was twisted in a way that had slipped past every prior search completely undetected. Understanding why it survived would require thinking about the universe as a musical instrument. The simplest version of a wrapped universe is the three torus. Picture a cube of space where the left face connects to the right face, the floor connects to the ceiling, and the front connects to the back. Walk far enough in any direction and you return to where you started, like a spaceship in an old arcade game that vanishes off one edge of the screen and reappears from the other side. The geometry inside this space is perfectly flat. Triangles still sum to 180 degrees. Parallel lines never meet. The only difference from an infinite flat universe is the global structure, the way the space connects to itself on the larger scales. Previous searches had set strong limits on this simple shape. If a three-torus universe is smaller than the sphere of the cosmic microwave background, matched circles should appear in the data at the corresponding angular scales. None were found. The simple three-torus appeared to be ruled out for any size smaller than roughly the distance to the last scattering surface. Then the compact team examined what happens when you apply a half-turn twist before connecting the faces. In the twisted version, opposite faces of the cube are identified after a rotation of 180 degrees. When you travel through one face and emerge from the opposite side, You arrive flipped. The geometry is still flat, still consistent with everything measured about local curvature. But the patterns of correlation this topology produces in the cosmic microwave background are fundamentally different from the simple, untwisted version. And those different patterns are dramatically harder to rule out. The compact analysis found that this twisted topology, labeled as the second of 18 mathematically distinct flat topological spaces, remained consistent with the data even when the fundamental domain was far smaller than the observable sphere. The reason is subtle but consequential. The twisted identification between faces creates correlations between distant points in space, but those correlations appear in different statistical forms than simple matched circles. Standard tests designed to find ordinary matched circles pass through this topology essentially blind. Oliver Philcox, commenting on the finding, noted that there are many possible ways the universe could be topologically connected, and that it remains genuinely difficult to eliminate them. That statement captures something important. Every time cosmologists announce that some version of a wrapped universe is constrained, they mean specifically the version they tested. The catalogue of possibilities contains far more shapes than any single search has examined. Similar results applied to yet another twisted variant, a version where the connecting rotation is 90 degrees instead of 180. This topology also survived the existing constraints. And for related reasons, the non-trivial phase relationships it creates between different regions of space are different enough from simple translational symmetry that standard searches miss them entirely. These were members of a mathematically complete catalogue of all possible geometrically flat universes, not exotic edge cases invented to rescue a failing theory. If the universe is flat, which evidence strongly suggests, then any of these 18 shapes is a legitimate physical candidate. Most had received essentially no examination. The compact team was methodically working through the entire catalogue, and what they were developing to do it was a new way of listening to space itself. In 1966, a mathematician named Mark Kac published a paper with one of the most memorable titles in the history of his field. He called it, "Can One Hear the Shape of a Drum?" The question seemed playful. The mathematics behind it was serious and deep. Different shaped drums support different characteristic vibrational modes. A rectangular drum resonates differently from a circular one. A triangular drum produces a completely different set of frequencies. The question was whether those frequencies alone, the sound alone, contained enough information to reconstruct the physical shape of the instrument. The answer, it turned out, was mostly yes, with some subtle exceptions. Decades later, the compact collaboration recognized that the identical logic applies to the universe itself. Every topology has a unique set of allowed frequencies, the modes that can fit within the finite space it defines. A 3-torus universe supports waves of certain sizes and orientations, determined by the dimensions of its fundamental domain. A dodecahedral space supports completely different waves, shaped by its pentagonal faces and their connecting rotations. A simple infinite flat universe, by contrast, supports every frequency without restriction. Each topology is a different instrument, and the cosmic microwave background is the music that instrument has been playing since the universe was 380,000 years old. The compact team built what they call correlation matrices. For a given topology, with a given size and orientation, you can calculate mathematically what the cosmic microwave background should look like. Specifically, you can predict the statistical correlations between temperature fluctuations at different points across the sky. Different topologies produce different patterns. Some suppress correlations at large angular separations. Others introduce correlations between points on opposite sides of the sky. Twisted topologies produce correlations that rotate between sky patches in ways characteristic to their specific twist angle. Once you have the predicted correlation matrix for a topology, you compare it against actual data from the Planck satellite. If the topology matches the real universe, the agreement should be clear. If the topology is wrong, the mismatch appears. Run this comparison across the full catalogue of possible flat topologies, and you have a systematic survey that would have been computationally impossible just 10 years ago. The team extended this approach in multiple directions. They analyzed orientable topologies, where a traveler moving through space returns to the starting point in the same orientation, and non-orientable topologies, where returning from a journey leaves you mirrored with left and right reversed. They built predictions for how different topologies would affect the polarization patterns in the cosmic microwave background, not just the temperature fluctuations. They applied machine learning algorithms, training computational classifiers on synthetic universes with known shapes, teaching models to recognize topological fingerprints, the same way an image classifier learns to distinguish handwritten letters. Craig Copey returned repeatedly to the large-angle correlation anomaly in the cosmic microwave background. The observed fact that temperature fluctuations show essentially no correlation for angular separations greater than 60 degrees, when the standard model predicts substantial correlation all the way to 180 degrees. A finite universe with a compact topology would naturally suppress the vibrational modes responsible for those large-angle correlations, cutting them off in a way that matches what telescopes have been measuring for decades. The music metaphor had real mathematical content. The universe was playing a song, and specific notes were missing. The compact method was designed to determine what shape of instrument produces exactly that silence. What the James Webb Space Telescope was about to reveal would make answering that question far more urgent. Something was wrong with the early universe. The James Webb Space Telescope had been built to look farther back in time than any instrument before it, to push observation to the very first galaxies that emerged from the primordial darkness. The standard model made specific, confident predictions about what those first structures should look like: small, irregular, chaotic, and sparse. Seeds of future complexity, not yet bloomed. The universe just a few 100 million years after the Big Bang should resemble a rough draft, not a finished work. Webb looked, and it found something that looked disturbingly finished. The standard picture of galaxy formation rests on decades of theoretical development and observational confirmation. Galaxies grow hierarchically. Small structures form first under the pull of gravity, then merge over hundreds of millions of years into larger ones, like towns gradually absorbing surrounding villages to become cities. The very earliest universe should contain only small, chaotic proto-galaxies, seeds that will eventually grow into the grand spirals and massive elliptical structures we observe in the relatively nearby cosmos. The galaxies Webb found at the greatest distances looked nothing like seeds. They looked like mature trees. One galaxy sits at such an extreme distance that its light traveled 430 million years to reach the telescope. It formed when the universe was a tiny fraction of its current age. Its stellar mass, the total weight of all the stars packed inside it, far exceeds what the models said should be possible at that era of cosmic history. Dozens of other galaxies confirmed at similarly extreme distances tell the same story. Their mass, their organization, their apparent completeness, all of it defies the standard timeline for how matter organizes itself under gravity. Researchers proposed that perhaps these early galaxies converted their available gas into stars with extraordinary efficiency. The calculation came back unfavorable. Getting these structures to their observed masses within the available time required converting essentially all available gas into stars with nearly perfect efficiency, something that violates what physicists understand about how star formation works under any known physical conditions. A 2023 paper by Alan Coley and his collaborators stated the situation without diplomatic softening. Such massive galaxies, the paper noted, do not have enough time to form within the standard cosmological model. These observations significantly challenge standard cosmology. Michael Boylan-Colchin at the University of Texas in Austin ran the numbers independently and reached the same conclusion. Some of what Webb was finding required conditions that standard physics simply does not permit. Something fundamental in the model was producing the wrong predictions. This was a structural failure. The early universe was assembling massive galaxies faster than the laws of physics as currently understood should allow, and no simple adjustment to the existing framework would repair the mismatch. What made this relevant to the shape of the universe would become clear with time. Galaxy formation is one domain. Cosmic topology is another. But when a foundational model fails in one domain, everything constructed on top of it becomes suspect. And the standard cosmological model carried within it a very specific set of inherited assumptions about the geometry of space itself, assumptions that had never been independently tested but had traveled along silently inside the framework from the beginning. The problem ran deeper than anyone had yet recognized. They appeared in the Webb data as small, intensely red smudges scattered across images packed with the light of the early universe. Nobody had predicted them. No existing theory had reserved a place for them. Astronomers began calling them little red dots, a casual name for objects that turned out to carry serious implications. The little red dots are supermassive black holes. That much became clear relatively quickly from their spectral signatures. Supermassive black holes exist at the centers of most large galaxies in the nearby universe, so their existence in principle is not surprising. What makes the little red dots deeply unsettling is their timing and their size. They are accreting mass at furious rates just 600 million years after the Big Bang, and they are enormous, far larger than they have any right to be given how little time the universe had been in existence when they appear. In the nearby universe, astronomers have established a consistent relationship between the mass of a central black hole and the total mass of its host galaxy. The black hole accounts for a small fraction of the stellar mass. This relationship appears to emerge naturally from the way black holes and their surrounding galaxies co-evolve over billions of years, each regulating the growth of the other through feedback processes. It is one of the most robust correlations in observational astronomy. The little red dots shatter this relationship entirely. Their black holes outweigh their host galaxies by factors of 100 to 1,000 times compared to what nearby universe observations predict. The black hole grew faster than the galaxy surrounding it. In some cases, the black hole appears to dominate the entire structure, with the surrounding stars almost incidental. Then came one discovery that crystallized the problem more sharply than any other. A galaxy now known as Virgil was described by researchers at the University of Arizona in 2025 as a cosmic shapeshifter. George Rieke, a pioneer of infrared astronomy who helped design the instruments aboard Webb itself, was direct about what the telescope had revealed when studying this object. He stated that the James Webb Space Telescope had demonstrated that ideas about how supermassive black holes formed were pretty much completely wrong. That is not careful hedging from a cautious scientist. Rieke has spent decades designing instruments to examine the universe at wavelengths invisible to the human eye. When he says formation models are completely wrong, the weight of that statement is substantial. Growing a black hole to that mass, in a universe that young, requires exceeding the physical limits on how fast infalling matter can be swallowed before radiation pressure pushes it back out. Standard astrophysics offers no comfortable explanation for what Webb was observing. The proposed alternatives, including black holes that form directly from collapsing gas clouds rather than from dying stars, require modifications to the early universe that ripple through the entire cosmological framework. Every modification proposed to explain the little red dots touches assumptions that extend outward into the broader model. Assumptions about how dark matter behaves. Assumptions about the initial conditions from which all structure grew. Assumptions that the cosmological framework inherited without question and built everything else upon. The thread was pulling, and the next discovery would show how deep the unraveling went. The first galaxies in the universe were supposed to be roughly round. Gravity pulls inward from a central concentration of mass, drawing in gas and dark matter in a spreading sphere. Early structures might be irregular and chaotic in detail, but the standard models consistently predicted that the very first galaxies would lack strong elongation. The cosmos in its infancy should appear lumpy and compact, without the stretched, thread-like forms that appear later as the cosmic web develops over billions of years. Webb looked at the early universe and found something else entirely. A 2025 study led by Álvaro Pozo at the Donostia International Physics Center in Spain, with contributions from Rogier Windhorst at Arizona State University and a broader team of collaborators, analyzed the shapes of early galaxies captured by the James Webb Space Telescope. The conclusion was striking. Many of these galaxies showed markedly elongated, filamentary morphologies. They were stretched, extended along preferred axes. They looked less like early compact blobs and far more like cosmic threads that had no business appearing so early. The standard cold dark matter model could not reproduce these shapes in its simulations. In standard simulations, the earliest structures form in patterns that do not generate the degree of elongation that Webb was observing. The mismatch was clear and consistent. One alternative explanation fit considerably better. Wave dark matter, sometimes called fuzzy dark matter, is built on the idea that dark matter is composed of ultralight particles, so extremely light that quantum mechanical effects operate on astronomical scales. These particles behave less like a collection of individual microscopic bullets and more like a fluid governed by wave equations. Quantum pressure resists compression in ways that classical particle dark matter does not experience, creating characteristic structures with smooth central regions and suppressed small-scale clumping. On large scales, this wave-like dark matter tends to organize along quantum interference patterns, naturally producing elongated, filamentary structures of precisely the kind Webb was finding in the early universe. This finding matters far beyond the question of what dark matter is made of. If dark matter behaves as waves rather than particles, the initial distribution of density fluctuations across the early universe is fundamentally different from what cold dark matter predicts. The seeds from which all galaxies grow are shaped differently, suppressed on certain scales in ways that cold dark matter does not produce. The entire history of how large structures assemble through cosmic time changes with it, and the power spectrum of those initial density fluctuations is the identical quantity that cosmologists use to constrain curvature and to search for topological signatures in the cosmic microwave background. A modification to the nature of dark matter that changes the power spectrum does not stay confined to galaxy formation. It changes the input to every measurement the field uses to assess the geometry and topology of space. The discovery of filamentary early galaxies was therefore connected to the topology question in a direct and consequential way. It was another component of the same larger problem. When the dark matter model needs revision, the cosmological model needs revision, and a model under revision cannot simply inherit its geometric assumptions unchanged from a prior version of itself. Something deeper in the foundations was shifting. For years, two groups of astronomers have been measuring the same fundamental number and getting answers that disagree by 4 to 5 standard deviations. The number is the Hubble constant, the rate at which the universe expands. It describes how fast distant galaxies move away from us, and it is one of the most foundational quantities in all of cosmology. Both groups are careful. Both have published their methods in detail. Both have checked and refined their results through multiple rounds of independent verification. They still disagree, and the gap between them has not closed. The first group uses the cosmic microwave background. By fitting the standard cosmological model to the pattern of temperature fluctuations in that ancient light, they extract a Hubble constant of roughly 67 to 68 kilometers per second for every million light-years of distance. This is the early universe measurement, anchored in physics from just 380,000 years after the Big Bang. The second group uses the cosmic distance ladder. They measure pulsating stars called Cepheid variables in nearby galaxies, calibrate those measurements to the distances of exploding stars called supernovae, and use those supernovae as standardized cosmic rulers to measure the expansion of the present-day universe directly. Their result lands at roughly 73 kilometers per second per million light-years, substantially higher than the early universe value. That discrepancy is called the Hubble tension. At 4 to 5 standard deviations of significance, it is large enough that in almost any other branch of science, it would constitute a confirmed discovery of something new. Something is wrong in the model somewhere. Cosmologists have been searching for the source for years. One underappreciated dimension of this tension connects directly to the curvature of space. There is a well-documented geometric degeneracy embedded in the cosmic microwave background data. A closed universe with a lower Hubble constant and a slightly higher matter density produces temperature fluctuation patterns that are nearly indistinguishable from a flat universe with a higher Hubble constant and a lower matter density. The two models are virtually identical in the data the Planck satellite gathered. This means the apparent measurement of the Hubble constant from the cosmic microwave background is entangled with the assumption of flatness in a way that is rarely acknowledged in public discussions of the tension. Eleonora Di Valentino and her colleagues argued explicitly that assuming a flat universe could be masking a deeper crisis. A universe that is slightly closed, with the mild curvature that Planck data alone suggests, would naturally produce a lower apparent Hubble constant from cosmic microwave background analysis. The local measurements, which carry no such geometric assumption, land at the higher value. The tension between those two numbers could therefore reflect, at least in part, the fact that the universe carries non-trivial geometry that the standard model is not accounting for. Non-trivial topology complicates this further still. Different topologies modify the effective power spectrum of the cosmic microwave background in ways that shift-fitted cosmological parameters, including the Hubble constant. A universe with a compact topology could appear to prefer a different expansion rate. The expansion itself might be the same. The difference would come from the topology altering how the data gets interpreted within a framework that assumes no topology exists at all. The Hubble tension might be a crack in the foundation, or it might be a window into something stranger. The standard cosmological model has a formal name, lambda cold dark matter. Lambda is the cosmological constant, the energy inherent to empty space that drives the accelerating expansion of the universe. Cold dark matter is the dominant form of invisible matter, slow-moving particles that clump under gravity and form the invisible scaffolding on which all visible structure assembles. Together, combined with ordinary matter, radiation, and the geometry of a nearly flat universe, these ingredients describe a framework that has matched an extraordinary range of observations across decades of careful measurement. It is also, increasingly, a framework under siege. Every anomaly the James Webb Space Telescope has revealed adds weight to the same conclusion. Galaxies too massive and too mature in the first few 100 million years after the Big Bang. Black holes too large for their host galaxies at extreme redshifts. Morphologies that cold dark matter simulations consistently fail to reproduce. A universe that assembled its large structures faster than the standard timeline permits. No single anomaly is lethal by itself. For each individual discrepancy, astronomers can propose modifications, push parameters, or invoke new physics in a targeted way. But the anomalies are arriving in a cluster, all pointing in the same direction, all indicating that something in the foundations is producing wrong predictions. Modified gravity represents one class of response. If gravity itself behaves differently on large scales than general relativity predicts, the rate at which structures grow changes. Galaxies could assemble faster, black holes could grow faster, but modifying gravity does not leave the curvature of space unchanged. A different gravitational law produces a different geometric relationship between matter, energy, and the shape of space-time. Curvature measurements derived from the standard framework inherit the standard gravitational law and would shift if the law is wrong. Early dark energy is another proposal. If an additional form of energy was present in the universe during its first few 100 million years, the expansion history before galaxies formed would be different. The cosmic yardstick used to interpret the microwave background would change, and changing that yardstick shifts the apparent value of the Hubble constant, potentially easing the tension with local measurements. But early dark energy also modifies what curvature measurements mean, because curvature is extracted from the same observational data using the same expansion history that is being revised. Wave dark matter changes the initial power spectrum of density fluctuations, the same spectrum that topology searchers use as their baseline for comparison. What unifies all of these possible extensions of the standard model is a single, uncomfortable truth. Lambda-cold dark matter is not merely a theory of galaxy formation. It is a global framework connecting measurements of the cosmic microwave background to measurements of large-scale structure to the geometry of the universe. Every component is connected to every other component. When one part is wrong, the corrections propagate outward into everything else. De Valentino and her colleagues had written exactly this conclusion. The assumption of a flat universe, they argued, could mask a cosmological crisis where disparate observed properties of the universe appear mutually inconsistent. The universe was not waiting for a clean solution. It was accumulating inconsistencies faster than any single fix could absorb. And the most comprehensive map of the early universe ever assembled was about to add one more indispensable layer to the evidence. In June 2025, an international team of more than 200 scientists released a catalogue that redrew the three-dimensional map of the observable universe in a single document. The project was called Cosmos Webb. It was built from 250 hours of observation time on the James Webb Space Telescope, pointed at a carefully chosen patch of sky, covering an area several times larger than the full moon. The resulting catalogue, led by Marco Shuntov at the Cosmic Dawn Center in Copenhagen, contained the positions, distances, masses, and shapes of 780,000 galaxies. It was the largest, deepest, most complete three-dimensional survey of cosmic structure ever assembled. Every object in that catalogue was a data point in the ongoing argument about what the universe actually looks like at its largest scales. Previous galaxy surveys had been powerful, but limited in different ways. Ground-based instruments had mapped hundreds of millions of galaxies in the relatively nearby cosmos, but could not reach the distances where the early universe's large-scale structure would be most revealing. Webb pushed that boundary dramatically. The Cosmos Webb catalogue extended to redshifts of approximately 7, capturing galaxies as they appeared when the universe was less than 1 billion years old, a small fraction of its current age of 13.8 billion years. What the catalogue confirmed, in the most unambiguous terms yet achieved, was the anomalous abundance of massive galaxies in the early universe. Smaller Webb surveys had already hinted at the problem. Some skeptics had suggested the early results might reflect incomplete data, cosmic flukes from limited sample sizes, or subtle calibration errors that would vanish with more coverage. The Cosmos Webb catalogue, with its 780,000 objects spread across a large, continuous, uniformly observed area of sky, removed those doubts systematically. Massive, organized galaxies existed in the early universe in numbers that the standard model cannot account for. The abundance was a feature of the universe, not an artifact of the survey, but the catalogue offered something beyond confirmation. By mapping the three-dimensional arrangement of galaxies across an enormous volume at extreme cosmic distances, Cosmos Webb provided precisely the kind of data that the compact collaboration needed to extend its search for topological signatures far beyond what the cosmic microwave background alone could offer. The microwave background provides a two-dimensional snapshot of the last scattering surface, a single shell of ancient light encoding information from one specific moment in cosmic history. Galaxy surveys fill the full three-dimensional volume of space, providing information from a vast range of cosmic distances and times. A universe with a compact topology would leave specific imprints in that volumetric data. Galaxies in one region of the survey would show correlated patterns with galaxies in apparently distant regions, because the topology wraps space so that distant points are actually connected through the fundamental domain of the universe. These correlations have geometric signatures dependent on the size and shape of that fundamental domain, signatures that become more detectable as the survey area and depth increase. With 780,000 objects extending to the depths that Webb could reach, the potential power of a topological search multiplied dramatically compared to any previous dataset. The question of cosmic shape had moved beyond pure theory. The data needed to answer it was arriving. The mathematical tools to analyze it had been built. The collaboration to conduct the search was already at work. What they might find would change everything we think we know about the universe we live in. The assumption hiding inside almost every cosmological model is enormous. Most scientists, when pressed, will admit they assume the universe is infinite. Space goes on forever in every direction, never ending, never curling back, expanding outward without limit. It sounds clean, almost obvious. But when you follow this assumption to its logical conclusion, the universe becomes something deeply troubling. An infinite universe contains infinite matter, infinite galaxies, infinite gas clouds, infinite versions of every planet that has ever formed. And here is where the trouble begins. If space extends forever and matter is distributed randomly within it, then every possible arrangement of matter must appear somewhere, given enough room. Every configuration, every combination, every accident of physics that could occur will occur in infinite places, infinite times. That includes you. In an infinite universe, there is not just one version of this moment. There are infinitely many. Somewhere, separated from you by a distance so vast no light could ever cross it, an exact copy of you exists, listening to these same words. Somewhere else, a version of you made a different choice last Tuesday. Somewhere else, the stars aligned differently, and you were never born at all. This sounds like philosophy. Physicists take it seriously because mathematics forces them to. The problem deepens when you ask a simple question. What is the probability of anything in an infinite universe? This is called the measure problem in cosmology. In an infinite space with infinite copies of every event, how do you calculate the likelihood of your own existence? How do you assign meaning to any prediction when every outcome, however improbable, happens infinitely many times? The mathematics collapses. Physicists consider this one of the most severe conceptual failures in modern cosmology, and it has no agreed solution. The problem only arises because the universe is assumed to be infinite. Then there is the Boltzmann brain. Ludwig Boltzmann, the 19th century Austrian physicist who built the mathematics of heat and disorder, showed that in any system given enough time, random fluctuations will eventually assemble extraordinary configurations of matter that appear structured. In an infinite universe with infinite time, such fluctuations will eventually, randomly, produce something resembling a complete human consciousness, a disembodied brain floating in empty space, convinced it perceives a real world around it. These are called Boltzmann brains. An infinite universe produces infinitely many of them. The disturbing implication is that these randomly generated observers vastly outnumber real ones, which means the odds suggest you might be one. Floating in void, dreaming, no cosmologist genuinely believes this, but no one has cleanly resolved it either. The infinity assumption also makes cosmology unpredictable at its deepest level. You cannot run statistics on infinity. You cannot measure a probability that has no denominator. Physics, at its core, is the science of measuring things, and an infinite universe defeats measurement before it begins. These are the consequences of the assumption almost no one questions aloud. An infinite universe is elegant on the surface and catastrophic underneath. And here is what makes the search for cosmic topology so extraordinary. It offers a way out. A finite universe with a wrapped topology sidesteps the infinity problem entirely. The measure problem dissolves. The Boltzmann brain paradox loses its teeth. Statistics become meaningful again. Physics can predict again. The scientists searching for the shape of the universe are doing something far more important than satisfying academic curiosity. They are trying to rescue the most fundamental tool humanity has ever built, the ability to understand anything at all. But a finite universe raises its own strange questions. and what it might look like from the inside is unlike anything you have imagined. Flip the assumption. Suppose the universe is finite, closed, and wrapped back on itself. Suppose it is more like the surface of a sphere than an endless plane. Then, something extraordinary follows from basic geometry. Something that should stop you cold. Light would travel in loops. In a finite, multiply-connected universe, a beam of light traveling in one direction would eventually complete a circuit and arrive back from the opposite direction. It would not hit a wall. There are no walls. It simply follows the curvature of space back to where it began, the way a ship sailing west eventually returns from the east. The universe has no edge to find, because it wraps. Now consider what that means for what we see. Every object in such a universe would have multiple images. A distant galaxy whose light has had time to circle the universe would appear in multiple locations in the sky. The same physical object seen from different angles, at different moments in its history. The universe would become, as French cosmologist Jean-Pierre Luminet described it, a cosmic hall of mirrors. The same small region of space, reflected and repeated in every direction, creating the illusion of a vast and varied cosmos that is actually a single finite room seen over and over. This is not a fantasy. It is a mathematically rigorous consequence of certain topologies, and the terrifying part is that we might already be inside it without knowing. Think about what that would mean for every sky survey ever conducted, every catalogue of distant galaxies, every deep field image showing thousands of objects scattered across the sky. Some of those objects could be the same galaxy, seen at different ages, from different angles, appearing as entirely separate structures because no one yet knows where to look for the repetition. The universe might be far smaller than it looks. The observable cosmos might be the same neighborhood photographed from 1,000 different windows. Jean-Pierre Luminet put it precisely. Physical space can be closed, small, and multiply connected, yet have the illusion that the observed space is greater. In such a universe, you would also be seeing your own galaxy in that vast array. Billions of years ago, when it was young and chaotic, before the stars that built our world had even ignited, a galaxy that is us would appear somewhere in the deep field images. Unrecognized because it looks nothing like what it will become, we have been photographing our own past and filing it away as someone else's story. A finite wrapped universe also solves the infinity problem. The total amount of matter becomes countable, at least in principle. The Boltzmann brain paradox disappears. The measure problem resolves. Physics can breathe again, but the finite universe hypothesis carries its own demand. If it is true, there must be evidence. The cosmic microwave background, the oldest light in existence, must carry fingerprints of the universe's shape. Those fingerprints would show up as matched patterns, identical temperature fluctuation sequences appearing in separated regions of sky, because they represent the same physical point seen from different directions. That test is being run right now. The results are not yet definitive, but the signals that have appeared in the data are stranger than anyone expected. And one of them looks like a scar from something that happened long before our universe existed. Inflation never truly stopped. That is the uncomfortable implication of the most widely accepted extension of inflationary cosmology. In eternal inflation theory, the mechanism that drove the universe's extraordinary expansion in its first fraction of a second did not shut off cleanly. It continued, and it continues still, in regions of space so remote that no signal from them could ever reach us. Space keeps spawning, ceaselessly, in an endless landscape of expansion. Occasionally, within that landscape, a pocket of space stops inflating locally. It becomes a bubble, a region where the laws of physics settle into stable values, where matter can form, where stars and galaxies can grow. Our universe is one such bubble. Other bubbles exist, each with its own physical constants, each with its own geometry, each with its own history, playing out in complete isolation, separated from every other bubble by an expanding void that no form of communication could ever cross. This is not established fact. It is a theory, grounded in mathematics, taken seriously by some of the most careful thinkers in cosmology, and it connects to the shape of our universe in a way that is difficult to dismiss. If other bubbles exist, they can collide with ours. Not often, the odds are small over any finite time. But over infinite time, in an infinitely expanding landscape, collisions happen. And when two bubble universes crash into each other, the impact leaves a mark. The mark would be visible in the cosmic microwave background. It would appear as a circular disc-shaped anomaly, a region where the ancient light looks subtly different from everything around it, where the temperature pattern has been disturbed in a precise geometric way. Researchers Stephen Feeney, Matthew Johnson, Daniel Mortlock, and Hiranya Paris worked out the mathematics of bubble collisions in 2011. Their models showed exactly what such scars should look like. Then recall the cold spot, that 5-degree circle in the southern sky, colder than anything around it by 150 millionths of a degree. It sits in the data unexplained, surviving every analysis, resisting every mundane accounting. The supervoid hypothesis does not fully explain it. Systematic errors have been ruled out multiple times. It is real, and it is strange. One possibility remains on the table. The cold spot is a scar, a bruise left on the fabric of our universe by a collision with another bubble, another cosmos that grazed ours in the early moments of existence and then separated forever. The temperature anomaly would be the echo of that impact, preserved in the oldest light we can see. If that is what the cold spot is, then we have already seen evidence of the multiverse, not confirmation. Evidence, a signal sitting in plain sight for decades, labeled an anomaly, waiting for the interpretation that explains it. The universe's shape and the multiverse's existence are bound together in this single question. A finite bubble with a specific topology implies other bubbles. Scars in the ancient light imply collisions, and the cold spot, still unexplained after 20 years of study, sits there like a question mark stamped into the earliest record of reality. Whatever created it, it means our universe is not alone in some profound sense. And that changes what it means to ask about the shape of the space we live in. Max Tegmark, the Swedish-American physicist at the Massachusetts Institute of Technology, offered an idea that sounds like science fiction and lands like a hammer. He called it the quilted multiverse. The logic begins with a single assumption: space is infinite. If space is infinite, and matter is distributed according to the laws of quantum mechanics, with random variations from place to place, then every possible arrangement of matter must appear somewhere. There are only so many ways to arrange particles within a given volume. Given infinite volume, every arrangement repeats, not just similar arrangements, exact copies. This means there is a region of space, some unimaginable distance away, where every particle in your observable universe is arranged identically to how it is arranged here. Every galaxy in the same position, every atom in the same configuration, every thought in every brain is the same thought. That region is, for all purposes that matter, another you, and beyond that, there are infinite more. The quilted multiverse is not a separate dimension. It is not another universe in some exotic sense. It is simply what an infinite universe mathematically guarantees, given random initial conditions. The multiverse in this model is just the far reaches of the same single space you have always inhabited. Now here is the critical pivot. A finite, wrapped universe breaks this logic entirely. If space is not infinite, if it closes back on itself on some definite scale, then the quilt is not an endless expanse. It is one patch, one room, one finite arrangement that does not repeat because there is no infinite space in which to repeat it. Copies of you do not exist because there is no room for them. The universe is a single, closed, unrepeatable thing. To find evidence for a compact, multiply-connected topology would be to rule out the quilted multiverse. It would mean that you are not repeated anywhere, that this specific arrangement of matter This specific moment, these specific thoughts occurring in this specific mind, are singular, unique. They exist once and only once in all of physical reality. That is either terrifying or beautiful, depending on your temperament. The two possibilities, infinite and looping, lead to entirely different pictures of what existence is. In an infinite flat universe, every story has already been told infinitely many times and will be told infinitely many more. In a finite wrapped universe, every story is told exactly once, in one small room that only seems vast because the mirrors are so good. And there is a third option, which the data will not yet let us dismiss. The universe could be finite, but still large enough that its topology is invisible to any instrument we could build. In that case, the quilt might have copies, but they lie beyond any horizon we could ever observe. The singularity of this moment might be an illusion maintained by our own limitations. That is the maddening edge of the question. A discovery that could be the most profound in human history might also, in some scenarios, be permanently beyond reach. But the next decade brings tools that could change that, and they are closer to being ready than most people realize. The equipment being built right now was designed with exactly this question in mind. LIGHTBIRD is a satellite mission developed through a collaboration between the Japan Aerospace Exploration Agency and the European Space Agency, planned for launch around 2028. Its name stands for Light Satellite, for the studies of B-mode polarization and inflation from cosmic background radiation detection. The mission will measure the polarization of the cosmic microwave background with sensitivity, an order of magnitude beyond anything currently available. Polarization patterns in the ancient light carry information that temperature maps cannot access, and certain topological signatures are only visible in polarization data. LIGHTBIRD is, in part, a shape of the universe detector. On the ground, cosmic microwave background stage 4 is taking shape, an array of ground-based telescopes operating at microwave frequencies. It will improve on every previous measurement of the cosmic microwave background's temperature and polarization simultaneously. The resolution, the sensitivity, and the sky coverage will all exceed prior experiments by significant margins. If there are subtle topological signatures hiding in the ancient light that current instruments missed, Stage 4 is designed to find them. Meanwhile, Euclid has already launched. This European Space Agency telescope, sent into space in 2023, is currently mapping the three-dimensional distribution of galaxies across a region covering 15,000 square degrees of sky, reaching out to a redshift of roughly 2. That means Euclid is building the most comprehensive map of the cosmic web ever assembled, a full three-dimensional picture of how matter clumped and clustered over the last 10 billion years. A finite wrapped universe would leave specific imprints in this map, repetitions in the galaxy distribution that have no other natural explanation. The Nancy Grace Roman Space Telescope, planned for launch around 2027, will conduct deep infrared surveys complementary to the James Webb Space Telescope. Together, they will provide the earliest and most detailed views of galaxy formation ever achieved. spacex, a National Aeronautics and Space Administration all-sky spectroscopic mission, will measure the redshifts of hundreds of millions of galaxies, giving the topological search a dataset of a scale and completeness previously unimaginable. Each of these instruments is a new pair of eyes aimed at a question that has existed since Aristotle. Each generates a new type of data that the collaboration for observations, models, and predictions of anomalies and cosmic topology, the COMPACT team, has already begun preparing to analyze. The searches that failed in the past failed partly because the data was too limited and partly because the computational tools were too slow. Both of those barriers are falling simultaneously. The same decade that brings these new telescopes also brings machine learning techniques capable of searching millions of possible topological configurations in the time it once took to examine a handful. What was impossible 5 years ago is routine now. What is routine now will be trivial in 5 more years. The era of actually answering this question is not approaching, it has arrived. And what the collaboration for observations, models, and predictions of anomalies and cosmic topology plans to do with that era goes further than any search attempted before. The compact team, those 15 or so scientists spread across 7 countries, have never been content to search where the light is brightest. Previous topology searches concentrated on the simplest possible compact spaces, the three-dimensional torus being the most natural candidate, and looked for circles in the cosmic microwave background. When those circles were not found at the expected scales, many researchers concluded that compact topology was ruled out. The compact collaboration looked at that conclusion and found it incomplete. The simple three-dimensional torus is ruled out if its scale is smaller than the observable horizon. That much is established. But topology is not a single hypothesis. It is a vast landscape of mathematical possibilities. 18 distinct flat topologies exist. Hundreds of spherical topologies remain. And the compact team showed in their landmark Physical Review Letters paper from April 2024 that most of these had never been seriously searched. Several of the exotic flat topologies, particularly the twisted tori where opposite faces connect after rotating 180 degrees, survive all existing constraints, even when their characteristic scale is far smaller than the horizon we can observe. They remain viable. They have simply never been properly tested. Yashar Akrami, leading the mathematical analysis from the Institute for Theoretical Physics in Madrid, put the group's ambition plainly when speaking with science journalists. They will either find the topology of the universe or determine that the universe is so large that its topology cannot be detected with any tools currently available. Those are the only two acceptable conclusions. Everything in between is a failure to look hard enough. The collaboration's next phase extends the search to spherical topologies, including the Poincare dodecahedral space that Jean-Pierre Luminet first proposed in 2003. This is the soccer ball universe, with its 12 pentagonal faces, where opposite faces connect after a 36-degree twist, and where the characteristic scale sits at roughly 80% of the observable universe. That search was attempted in the early days of the Wilkinson Microwave Anisotropy Probe satellite, and the results were contested. Compact will revisit it with Planck data and better methods. But the most powerful expansion of the search will come from galaxy surveys. The cosmic microwave background provides a two-dimensional snapshot of one surface. Galaxy surveys fill the full three-dimensional volume of the observable universe with data points. The Euclid satellite, the Webb Space Telescope, and the spacex mission will together provide the kind of volumetric data that makes topological detection genuinely achievable. In a compact universe, the three-dimensional galaxy distribution carries the same fingerprints as the ancient light. Specific correlations between galaxy positions, separated by very precise distances, would appear repeatedly across the sky if the universe wraps. Compact has already begun preparing the statistical tools to search for those correlations. And underneath all of this mathematical machinery lies a set of anomalies in the oldest light that refuse to go away, that have persisted through every upgrade in data quality, and that topology would explain not as coincidence, but as physics. The ancient light has been trying to tell us something for decades. When the Wilkinson Microwave Anisotropy Probe satellite mapped the cosmic microwave background in the early 2000s, physicists noticed immediately that the largest features in the map behaved strangely. The quadrupole and octopole, the two longest wavelength patterns in that ancient light, were far weaker than any standard model predicted. They also pointed in the same direction, aligned to within 11 degrees of each other, a coincidence so unlikely under normal assumptions that researchers gave it a name, the axis of evil. Then the Planck satellite arrived with sharper eyes, and the anomalies did not disappear. They sharpened, the alignment persisted, the large angle correlations remained missing. The cold spot held its position. A hemispherical asymmetry appeared, showing that the universe looks slightly different in one half of the sky than the other. Gabriel Jung, Nabila Aghanim, and colleagues confirmed in a 2024 paper in Astronomy and Astrophysics that these anomalies appear at a level found in typically less than 1% of simulated maps based on the standard cosmological model. Less than 1%. That means if you built 1,000 computer universes following the standard rules and checked each one, fewer than 10 would show what we actually observe. Craig Copey of Case Western Reserve University, a founding member of the Compact Collaboration, explains the connection to topology with one precise analogy. A taut string can only vibrate at wavelengths up to twice its own length. Notes longer than the string simply do not fit. A finite universe works the same way. It cannot contain fluctuation modes larger than its own size. If the universe wraps at a scale near the observable horizon, large-scale correlations would be suppressed above a certain angular scale. They would drop to essentially zero, and that is exactly what the data shows. The angular two-point correlation function of the cosmic microwave background falls to zero at angles larger than roughly 60 degrees, precisely where a compact universe would cut it off. In a standard infinite universe, this is a troubling mystery. In a finite, wrapped universe, it is the expected signal. The universe is showing us its walls, in the only way walls invisible to direct observation can show themselves, by the notes they prevent the cosmos from playing. The axis of evil alignment would also follow naturally. In a compact space, the largest surviving fluctuation modes align with the geometry of the topology itself. The universe has a preferred orientation baked into its shape, and the ancient light preserves it. The hemispherical asymmetry, the cold spot, the missing large angle power, all of them become not anomalies, requiring explanation, but inevitable consequences of living inside a finite, curved, and multiply-connected space. The oldest light in existence is not broken. It is a message, and the message has been sitting in the data, waiting for the right question to unlock it. Here is what the universe might actually look like. Start with what is measured. The local geometry is nearly flat, consistent with Euclidean space to within 0.5% across every precision measurement ever conducted. Triangles drawn between galaxies sum to 180 degrees. Parallel lines do not visibly converge. The curvature parameter sits close to zero in every combined analysis of cosmic microwave background data and galaxy survey data. But the word local carries enormous weight. When Planck data is examined alone, without combining it with other surveys, the curvature hints at something slightly closed. The value omega minus k arrives at negative 0.012 plus or minus 0.010 in the most recent analysis. That central value is consistently on the closed side. Slightly, persistently, the hint has softened with better data, but it has never vanished. Now add the global picture. The anomalies in the ancient light point toward a universe with a characteristic scale near the observable horizon. The Compact Collaboration has identified several topologies that remain fully consistent with all existing data. The Poincare dodecahedral space, with 12 pentagonal faces and a volume roughly 80% of what we can observe, naturally explains the missing large-scale power in the ancient light. Several twisted torus shapes survive constraints that eliminated their simpler counterparts. A handful of positively curved spherical topologies remain unexplored. If the universe wraps, it does so at a scale close enough to the observable edge that the wrapping is visible as subtle signatures in the statistics of ancient light and perhaps in the galaxy distribution when future surveys map it completely. The topology could be the soccer ball dodecahedron Luminet proposed. It could be one of the twisted tori the Compact team found still breathing after every search. It could be something not yet seriously analyzed, one of the many exotic shapes that computationally feasible searches have never reached. What would it feel like to live inside such a universe? Exactly like this. The local geometry would be indistinguishable from infinite flat space. No wall would ever appear. No boundary would make itself felt. Everything you could observe directly would look exactly as it does in the standard model. The difference would only emerge in the statistics, in the patterns, in the subtle repetitions of the same physical structures appearing at different angles and different ages, and perhaps in one detail more profound than any statistic. Somewhere in the deep sky, images already collected by the James Webb Space Telescope, somewhere in the hundreds of thousands of galaxies catalogued in the Cosmos Web Survey, there may be an image of our own galaxy, young, chaotic, unrecognizable, filed under a catalog number, assigned a redshift, measured and moved past. The cosmic hall of mirrors may have already captured us, and we simply have not yet found the frame that holds our reflection. The universe we might actually live in is finite, wrapped, and smaller than it appears. It only looks infinite because the mirrors are perfect. Imagine the moment. A team at a computing center, working through a dataset from a next-generation cosmic microwave background experiment, runs their correlation analysis for the 100th time. The code has been checked, rechecked, and checked again by people who do not want it to find something it did not actually find, and it finds it anyway. 6 pairs of circles in the ancient light, separated by precise angular distances, showing identical temperature fluctuation patterns rotated by 36 degrees. The signal is there in one dataset, then another, then a third analysis by an independent team on a different continent confirms it overnight. The universe is a dodecahedron. It wraps. It is finite. The size is known. The shape is known. Or perhaps the signal arrives differently. The Euclid satellite's 3-dimensional galaxy map, processed after years of careful observation, reveals that specific pairs of galaxies separated by precise co-moving distances are correlated in a way that has no natural explanation in standard cosmology. The same galaxy, imaged twice, the same cluster, repeated at a different angle and a different cosmic age. The fundamental domain of space, identified for the first time, projected across the sky in the distribution of light from a billion galaxies. Either way, the moment of discovery would be unlike any in the history of science. We would know that the universe is finite. We would know how large it is. We would know its shape, the specific mathematical object that describes the space all of existence inhabits. A question asked by Aristotle in 350 years before the Common Era, refined by generations of mathematicians and physicists, transformed into something measurable by the 20th century, and finally answered, what is the cosmos? What is its form? And then the implications would arrive in waves. Philosophy would have to grapple with a finite cosmos that contains all of physical reality. Theology would confront a universe that is bounded, shaped, specific, one mathematical object among the infinity of possible mathematical objects that might have existed and did not. The meaning of the word universe, defined since its coining as the totality of everything, would require revision because the totality of everything turns out to be a specific geometric structure with a name and a volume. Physics would face the consequence that most of what we call the observable universe is the same small region of space seen over and over from different angles and different times. Every survey, every redshift catalogue, every deep field photograph, all of it a series of reflections in a closed, finite, self-referencing chamber of space. The discovery would also confirm that humanity, from inside a small rocky planet orbiting an ordinary star in one galaxy, among billions of images of the same handful of galaxies, looked at the light of the oldest moment it could see, noticed that something was slightly wrong with the statistics, and followed that wrongness all the way to the shape of everything. That is what a discovery would mean. And it remains possible. The data has hinted at it for decades. The tools to confirm it are being built right now. The honest answer, as of this moment in the history of science, is that we do not know the shape of the universe. We know the local geometry is nearly flat. Every precision measurement of the cosmic microwave background, every survey of galaxy clustering, every analysis combining data from independent sources arrives at a universe that obeys Euclidean geometry to within a fraction of a percent. Triangles close, parallel lines hold, The rules of high school geometry describe the space around us to extraordinary accuracy. We also know that the global structure, the shape of the universe taken as a whole, as a single object in higher dimensional mathematics, remains genuinely undetermined. Flatness locally is consistent with an infinite plane, a finite cylinder, a torus, a twisted torus, a Klein bottle, or 17 other mathematically distinct structures. Measuring the curvature alone does not answer the question of shape. That distinction between geometry and topology is the most important thing the study of the cosmic shape has produced, and it is still not widely understood. We know the cosmic microwave background carries anomalies, the quadrupole and octupole alignment, the missing large-angle correlations, the cold spot, the hemispherical asymmetry. Each of these anomalies persists at the level where fewer than 1 in 100 standard simulations reproduces them. Their combination, appearing together in the same dataset, has a probability under the standard model of less than 0.1%. They have survived every improvement in data quality. They have sharpened with better instruments. They have refused, for over 2 decades, to go away. We know that the James Webb Space Telescope has proven the standard cosmological model is incomplete. Galaxies too massive for their age, black holes too large for their hosts, morphologies that match wave dark matter better than cold dark matter, a catalogue of 780,000 objects from the Cosmos Web Survey confirming that the early universe is doing something the standard model did not predict. When a model is wrong in one place, every assumption it contains must be re-examined. The assumption of flatness, the assumption of simple topology, the assumption that the universe extends without limit in every direction, forever. We know that the compact collaboration has demonstrated that most possible topologies have never been searched. Exotic shapes remain fully consistent with all existing data. The search has only just begun in any serious, systematic way. And we know that the instruments coming online in the next 5 to 10 years will push the search to a depth and precision that was computationally impossible even recently. Lightbeard will measure the polarization of ancient light with sensitivity no prior satellite could achieve. Euclid and the Roman Space Telescope will map 3-dimensional galaxy distributions across volumes of space, large enough to contain topological signatures if they exist. spacex will add the statistical power of hundreds of millions of measured galaxies. The compact team will run the analyses. Glenn Starkman of Case Western Reserve University, who has spent decades on this question, put it with precision. When it comes to the topology of the universe, we simply have no idea what to expect. That uncertainty is not a failure, it is an invitation. The shape of the universe is not a settled question, dressed in the language of open inquiry. It is genuinely, profoundly open. The answer is out there, encoded in the oldest light we can see, and in the distribution of every galaxy we have ever catalogued, waiting for the precise analysis that will finally extract it. Aristotle asked whether the cosmos has a limit. 2,300 years later, with the most powerful telescope in human history overhead and the most sophisticated mathematical collaboration ever assembled, working the data, the question remains open. But for the first time in history, we have the tools to answer it. The universe has a shape. We are about to find out what it is.